Can I get a little sense of you guys before I start? How many of you guys are students? I'm curious. And how many of you guys have data science on your business card? Got it. Interesting. How's the conference going so far? Yeah? Is it like too technical, not technical enough? That's what I always try to gauge with these talks. I never know how technical to go. Pretty technical? Pretty technical. And you want even more technical? Is that Nice. Well, all right. How many of you guys do machine learning in your day job? Oh, awesome. All right. Well, you might find this talk not technical enough. I won't be offended if you leave. So I'm Lukas. I used to work on machine learning algorithms at Stanford, and then at Yahoo, and then at a startup called PowerSet. And about 6 or 7 years ago, I started a company called Crowdflower. Anybody heard of Crowdflower? I'm curious. Anybody use Crowdflower? Nice. Awesome. Sweet. So Crowdflower, briefly, we have we crowdsource data collection. So we have people all around the world that can collect data for you. And so this supports a lot of machine learning tasks, because machine learning generally starts with training data, and often you need people to collect that training data. So I actually don't do machine learning in my day-to-day job, but I think a lot about machine learning because most of our customers are taking the data that we collect and using it to build machine learning models, and then doing a thing called human in the loop, where they take places where the algorithm's not confident and send it back to people. So I'm super passionate about making machine learning really work. And that's actually why I started Crowdflower. And I even have a couple graphs that are sort of the epiphany of why I started Crowdflower, which is, the first graph is the effect of better algorithms, which is what I really worked on in the beginning of my career. And I should really add neural net to this, but this is kind of, on the left you have a toy data set. Probably all of you guys have had this experience. I just did it with kind of vanilla scikit-learn on a document classification task. And you try naive Bayes, which is kind of like the simplest algorithm you could think of, and then maxent is maybe a little bit more machinery, and SVM is maybe a little bit more. And you could try a these days, right, like a CNN or something. But what happens is you don't get that much improvement really from the algorithms, right? I mean, here you have, on this data set, I went from 19% accuracy to 17% accuracy, which, if I was trying to publish a paper, I'd say, hey, that's over 10% error reduction, and that would be pretty exciting, right, if I was the first to come up with an SVM. But, in the real world, this isn't super helpful, right? A lot of our customers would look at this, if they're not actually data scientists or machine learning people, if they're kind of their boss, they'd say, well, 19% accurate classifier, can't really use that. 70% accurate classifier, well, still can't really use that. So I think what data science teams and machine learning teams spend most of their time really doing is feature selection. So I was actually surprised when I got my first job in industry. There was basically one person working on improving algorithms, and probably 30 or 40 people working on finding better features, right? So the feature selection process is kind of going from the data that you have to a set of numbers that you feed into your algorithm. So there's lots of different ways to do it, right? So unigrams is basically you look at every single word in your document and assign a number to it. Bigrams is a little more advanced, right? You look at each pair of words, and that can sometimes work better, right? If you say the word great, that probably means positive sentiment. But if you say, oh, great, that might mean, negative sentiment, right? So the pairs can have more information. And so, in the same task, I tried it with, I tried doing my classification with unigrams, and it's, 26% error rate. You try bigrams, and it goes down to 22%. Then if you combine unigrams and bigrams in this model that I had, it goes down to about a 17% error rate. And that's, that's kind of the typical thing that you see, right? The features often super, super helpful, often more helpful than, kind of optimizing your algorithm, finding the right parameters. But it's really hard to know what's going to work. I mean, I remember at Yahoo kind of working on document quality, I remember we discovered that semicolons were actually a pretty good predictor that the document wasn't like a crazy internet rant, right? Like people kind of pounding on their keyboards, they never really use semicolons. But they actually will. There's certain words that if they're misspelled, and they're misspelled with all capital letters, are like guaranteed. It's kind of a crazy internet rant that you wouldn't want to show high on your search results. So you look for these patterns, but I think this is really a big part of the art of machine learning, is finding what are the right features that make sense. And you see the paper on the right has kind of a similar outcome to me, where they see sometimes the bigrams are working better, sometimes the unigrams and bigrams are showing even higher accuracy, but then not always, right? Like they add parts of speech of the words, and that doesn't help with some of their classifiers. So these are the things that we don't do, right? This is what our customers do, but there's the thing that we do that almost always helps the accuracy of algorithms, which is the effect of more data, right? So here I had about 10,000 records that I showed my classifier, and then when it went up to 20,000, it actually went from 13% error rate down to 8%. And then when I showed it around 40,000, the error rate went down to a little over 4%, right? Which is a really meaningful result that I just got from adding more data to my training set. And there's actually a paper on the right, which I think is kind of funny, right? Because the point of this graph on the right, so it's the same axis, right? Where the y-axis here is error rate, so down is better. And they're basically showing, kind of red is the random thing, right? That's like the naive thing. And then the other colored lines are improvements, right? That actually got the paper published. And so they're showing that, like, okay, the green line is maybe, a couple percent improvement over the red line, right? And so they published the paper kind of saying that, and that's the point of this graph. But the kind of more obvious effect that they completely ignore is the fact that each time they add more training data, the error rate goes down a lot, right? So they start with 1,000 records, and I think they go up to 200,000. So it's log scale. But each time they basically add, an order of magnitude more training data, the error rate goes down more than the effect of the paper that they're publishing. And so you could say, well, you can't always add more data, but sometimes you can. And if there's cases where you can actually add more training data, you can do amazing things. There's actually one more effect that I think is kind of even more meaningful than more data. And actually, you can never find a paper that really talks about this. If any of you guys are actually in research, I think this is a really interesting research topic. So I can only show you kind of my anecdotal evidence. But we see it in almost every customer that we work with and everybody that we talk to, which is the effect of cleaner data is humongous, right? So here actually I went back through my data and I added noise. So I fed the classifier 90% accurate data, right? So 10% I kind of scrambled. And then the accuracy of the actual classifier itself is 12%, right? So the kind of input training data is only 90% accuracy, doesn't learn as good a classifier, right? That classifier is 12%. And then if it's 95% accurate data fed in, it's maybe 7% error rate, and then 4% with 100% accurate data, right? So this is a humongous effect, right? And this is potentially even easier to do than collecting more training data, and yet it's really rare that people want to go back over all the sets of data that they have and clean them up themselves, right? They think, oh, this is too much work, but the effect is powerful. And so, is there a question? Yeah. Yeah. Oh, yeah, let me try to repeat it because I'm actually having a little trouble hearing you. So I think you said in the real world, training data isn't always clean?
Though we clean the data while training the model, but the real data is not always clean.
Yeah. Yeah, so I mean, I guess if you mean, so I think there's sort of two types. I mean, in the real world, data is certainly messy, and you want it to kind of handle the messy cases. I think, though, if your labels are wrong, that's sort of like a different thing, right? So, say you're trying to, say you're trying to do face recognition, right? There is like a real thing that you're trying to do that I think someone could say, kind of, did you get that face recognition task right or wrong, right? So, I think that's there actually probably are cases that are not well defined for sure, right? But I think you can still kind of define the task as there is sort of like a platonic ideal of what you're trying to accomplish. And I think your testing data may also be not clean, right? And so, that may mess up your results, but that would kind of only underestimate the value of clean data, right? So, whatever you estimate on your test data, I think, by cleaning up your test data, it would even more show the effect of actually cleaning your training data. But I think there are other ways that you could clean your training data that would screw up the distribution. Like if you actually cleaned the underlying features, that wouldn't be something you'd want to do, right? Like, spell correcting your data, you definitely not want to do that, right? Because in the real world, people misspell stuff all the time. But yeah, good point. Yeah. If you train on unclean data and then you, you're saying you think that's true, or is the question?
Yeah, is that true? Because you already have 10% error. If you test 1% accurate,
I mean, I guess there's probably different situations. So the question is, if you trained on unclean data and tested on clean data, would you get better results? I mean, there's probably some mathematicians in the audience that would be better equipped to answer this. I mean, here's what I would say. Like, you'll get better results if you train on clean data. I'm really sure about that. Yeah, comment? Yeah.
I'd just like to make some suggestions. So the way I see things is, like what you just said, the data is fundamentally statistical. Meaning noise is
Yeah.
there's no deterministic point that you can into. Then it's only a matter whether your sample set is sufficient to deal with this statistical behavior. And then you can see that data you have. I can curve down vertically.
Yep.
But the gain of having more data actually will be
Plateau, yeah.
Yeah, at certain point.
Yep.
It will, because you already have sufficient data to measure those physical labels of parameters you want to measure in order to recognize or classify.
Yep.
And that's the way. So my thinking is actually you should live and die with noisy data, even from the training.
Okay, so here's the comment. Let me try to express it. So the point is kind of two things, right? One is that your data, the effect of more training data will plateau, right? And then the second point is that you should, because in the real world data is messy, you should take lots of messy data and use that to train your model. And so I guess I hear your point. I disagree. But I think this is something you can empirically test, right? So I'm sure there are situations where the amount of training data that you have plateaus. But I think it's a good thing to ask yourself, like, am I at a place where it's plateaus, right? Because certainly there's diminishing returns, right? So, as you get more and more data, the next piece of data matters less and less, right? That's undeniably true, right? But you still might want to get lots more data, right? Because if you get orders of magnitude more data, that effect might be good. And if you're paying millions of dollars for a machine learning team, maybe you should allocate some of that money to data collection and see, what if I really collected a ton of data, what would that do? So all I'd say is test it, right? I think we're all data people, we're all really empirical, right? So I think that's it's actually kind of a testable hypothesis. And I think another thing that I see is a lot of the really exciting advances in algorithms seem to me like they've come from the fact that data has become so plentiful. And in some situations, Facebook gets crazy amounts of data with the face labeled, right? And so they can do really, really interesting advanced things in facial recognition, right? Because they have data sets that when we were grad students, we'd only dream of, right? So I think even if you think you're at a plateau with your data, a new, more advanced algorithm might be able to actually use the fact that you have more data. But I think all I'd say is test it on your data. I would just encourage you to do that. And then the second thing is, does cleaning your data really help? I think that what you're actually trying to do with your data is usually pretty clean, right? You usually have a pretty clear idea of what you are trying to accomplish. And feeding in dirty examples, right, dirty feature sets, you definitely want to do, right? That'll make your model more robust. But I think actually cleaning the output of what you're trying to predict is typically helpful, but maybe not. I mean, I actually think, if you have examples where it's not, I'd be really interested in seeing them. But I'll say, what we see, what I saw with this particular data set and what our customers tell us is that when they clean their data, they often get better results. So, if you have any data sets or evidence, I'd love to see kind of more examples to put in this slide. I actually feel kind of bad that I don't have a kind of research paper to cite or show on the, the right side of this graph. This is definitely my own toy data, so you should be skeptical of my, my result here. But what I do know for sure is this next point, which is that people, data scientists spend most of their time cleaning up data, right? I mean, I think everybody kind of realizes this, right? In the last year or two, the media has really picked up on this. And I think that, whether you're doing modeling or business intelligence, if you input dirty data, it's not going to work as well. And data can get dirty enough to the point where you're actually, you can't build a good model, or the results that you're collecting on your data is actually wrong, right? So, I think what's for sure is companies hire lots of data scientists and machine learning people, and these machine learning people end up spending a lot of their time going through record by record cleaning up data. I know this is true because I was doing this, right? I was doing this in grad school. I was doing this, in my jobs after grad school. Like, I think everybody's had the experience of like opening up your data set, kind of looking for the weird outliers, taking them out or dealing with them in some way. This is like the real, what you end up really doing when you're actually trying to make a model work. And so, I'll just say like where I'm coming from, right? This is Crowdflower, and some of you guys, I guess, use it. And so we're a platform where you can kind of crowdsource the data cleanup and enrichment. So you can send out tasks to lots of people. So this is a vision task, right? Where you can, basically like label cars and trees and roads and things like that. But we do a lot of kind of NLP-based work where it's like, basically like categorize a piece of text, categorize an issue that one of your customers had, kind of all the different machine learning things that folks work on. And I just kind of want to talk about some of the data sets that we've collected. When we just first started our company, we had no customers and we had kind of a crowdsourced workforce. We wanted to try it. So, one of the fun data sets that we collected back in, I think, like 2009 was a color data set. So we basically showed people solid blocks of color and asked them, what would you call this color? Right? So, you might call the top one blue or sky blue and the bottom one red or purple or something like that. And, we created this visualization around what all the different people said, which I think is really kind of fun to look at, right? Like you kind of like, first you see, okay, people all call this stuff blue, but then you dig in deeper and it's like, there's like cerulean in here, and that's like a really tight circle. Like that's a color people have a really good sense of what it is. And we actually took that data set and put it online so that you guys could use it and people could do interesting analyses of it. And one of the first things that happened was this really nice guy at SAP went through and he cleaned up the data for us. And I think this is a great point. People are talking about like what, do you actually want to clean up a data set? And I think this really shows you how it depends. Like, we basically had a ton of misspellings and, a ton of weird stuff in here. Like somebody said, this color is baby poop, right? And like, this guy took that out. And it's like, well, do you want the misspellings? Like, do you want consistent capitalization? Really depends on the use case, right? So I was happy that this guy cleaned it up and published a second data set. It's almost better than open source in a way because the first version and the second version are useful to everyone. And then this guy Martin Wattenberg, who was at IBM at the time, I think, made this really cool visualization where you could see the size of the text is how many people said it. And then the location is sort of like the average of all the people that said that color, right? So this green is in some sense the average of all the things that people called green. And you can see that green is kind of the most popular thing to call a color, whereas turquoise is a little smaller and aqua is a little smaller than that. And we ended up doing this in a whole bunch of languages and comparing them, and I think it led to a lot of kind of interesting work. And then visualization companies started using it as a test data set for their tools. And then actually, some students took it and they made an app for colorblind people where you could look at a pixel and it would say, here's kind of the closest colors to that pixel. So, if you say like, okay, this is like considered to be sky blue, right? So it's not just like the normal kind of colorblind thing I think shows the red, green, blue values, but this actually showed kind of text of how people would describe the color. And then, we collected some other data sets over the years, like Apple Watch. We asked people, hey, what do you guys think about the Apple Watch? or actually this is labeling social media labels, the Apple Watch. And we sent it out to journalists and got all these different articles, right? So kind of fed people that kind of wanted to be data journalists data and saw what they did with it. So, one person says, okay, it gets a 55% approval rate. Another person, says, just slices the data to Texas, right? And so a Texas column that says, Texans aren't so thrilled about the Apple Watch. And then USA Today says, okay, women love Apple Watch more than men, right? Because they think that the apps are better. And so, we would publish these data sets from time to time, but, what we saw is that people were collecting the same data set over and over, right? So this is a while back. Someone was collecting there's 11,000 jobs that had the word sentiment in it, right? So there's just lots of people on the platform kind of collecting sentiment data sets. And we thought, I think a lot of these people would be willing to share it with each other if we made it easy. So we launched a thing saying, okay, we're gonna try to make data sets public so that people could use them. And we added a little button where you could say, okay, publish my data set. And, we in the first year or so, we got about 12 million data sets released, which felt good. But then we actually changed so we launched a Data for Everyone library that you guys can actually go to where you can download lots of interesting data sets that customers have collected that are labeled by people. And then, but then we actually changed our pricing so you can use Crowdflower for free if you make your data public, and that actually got tons and tons of adoption, right? So at that point, we got lots and lots of data published, and I really love it if folks like you actually go and use this, right? So we have an API where you can download all the data sets, and at this point, it's millions of data sets. In fact, I think it'd be a really interesting AI challenge to try to label all the different data sets at once, because it's kind of all the different things that people are building machine learning on top of, including URL categorization, kind of record data from various types of PDFs, extracting names and titles, which is a harder job than you'd think, summarizing articles, even like weird stuff like, is this image funny, right? So this is probably an unusual image labeling task that I'd be interested to see how well something could do. There's medical images, there's classifying attributes of people. And so, one of the things that we do with this is we run Kaggle competitions from time to time because we have all this data available. And I just thought this was a fun one because it's actually a search relevance data set. And I kind of worry in a world where training data is so powerful for making algorithms work, is it going to be hard for small startups and kind of upstarts to build high quality machine learning algorithms when they don't have that same core data? So we took a big chunk of data and we put it on Kaggle. And it was funny, in the first couple days, we saw that the baseline accuracy of just doing kind of the dumbest thing on this task was around 30%. And in the first 5 days, it went to a little over 60%. And I was really watching it, it was really fun, because I worked on search relevance in a different life, and I was thinking, I wonder how good they're going to get this classification. If in the first 5 days they've gone from 30 to 60%, maybe they'll get to 90% over the next month or two. And in fact, what happened is they were completely stuck, right? So it turned out getting to a little below 70% was actually really the maximum accuracy that they could get in the data set, despite tons and tons of teams trying, right? So this competition actually got more and more popular as time went on, but people couldn't break through the quality level they got in the first, significantly higher than the first couple days of the competition. Maybe because they weren't allowed to clean up the data or add training data. And so then, we were thinking about, what could we do? Because we see this all the time with our customers. I felt this, in my job, where you kind of get stuck at a certain level of accuracy and it's not good enough for the kind of thing that you want to do. And that got us really excited about human-in-the-loop computing. And so just to define human-in-the-loop computing, for those of you that don't do this, you basically start with an AI classifier. Where it's confident, you take the output, and where it's not confident, you send it to a human to get it annotated and you send it back, right? So this is a really good model if you can't get a classifier as accurate as you need for the task at hand. So, for example, labeling support tickets is something that a lot of companies wouldn't tolerate an accuracy below 99%, but that's probably too high of a reach for modern, kind of cutting edge natural language processing algorithms for many applications. But what you can do is you can say, okay, if I have an algorithm that's 80% accurate, but half the time it's super confident in its answer, and it's like always accurate, you can use that 50% where it's very high confidence, right? And now you've actually saved half of your cost using machine learning, and you don't have to worry about the fact that your algorithm is only 80% accurate. And so that's just the first part, right? The second part is, you're sending the not confident examples to humans to get them labeled, and there's a whole field that around kind of like what's a good label to get. And it turns out that basically the not confident labels are the best labels to feed back into your algorithm, right, in a process known as active learning. So you set up a labeling process here. Not only is this useful, right, but you have a labeling process now where your algorithm is going to get better and better much faster than if you were picking random examples to get labeled. And I think it's been interesting to see all the different ways that people are using active learning, because it really, really works, right? This is one of those things that you don't have to kind of squint your eyes to see the difference, right? So as you collect more data using active learning, you get order of magnitude effects on the power of the data that you collect, typically. And I think this is kind of studied from just a labeling perspective, but if you look at kind of real-world applications, you see really interesting human-in-the-loop applications, right? So you see self-driving cars have this Google published their metric of kind of miles per disengage, right? So in Google's case, the car is mostly driving, right? But every 4,500 miles or so, it actually hands control of the car over to a human, right, or it would crash, right? So the car isn't yet driving as well as humans, but it's kind of, has a human in the loop that it hands it over, right? And Toyota actually has a really different paradigm where the human is mostly driving, but they're trying to build a system that stops the car from crashing, right? So this is sort of using the algorithm in the case where it's just really, really confident something bad's going to happen. The algorithm actually takes control, right? So I think self-driving cars, again, it's an example where you need really, really high accuracy levels, higher than vision algorithms can get today, maybe. And so people switch to this human-in-the-loop model, and it works super well for them. There's also adaptive cruise control. And then I think advanced chess is super cool, right? So, I love games, and I remember when Deep Blue beat Kasparov. And it turns out that actually until really recently, if you wanted to make the best possible chess algorithm, you would still keep a human in the loop, right? So there's this thing called advanced chess where they actually have a human operator that's kind of using a computer to suggest moves. And in kind of closed positions or positions where the computer's struggling, the human operator would actually make the decision about the move to make. Right, so actually, I think this became, I've heard that this became not useful about a year ago, right? But it was about 20 years ago that Deep Blue really beat Kasparov. So those computers got better than the best human, but still humans stayed relevant for 20 more years in terms of making the best possible chess algorithm. And then I love Go. I grew up playing Go and kind of wanted to be a professional Go player when I was a kid. And it's really interesting to watch AlphaGo, beat the best, or maybe the best human. And I think again, it's interesting to see. I think the one game that the computer lost, it made a really, really funny mistake, right? So it won the match 3-1, but it made a really bizarre move that I think a human operator would have caught. So I think you actually saw in the playing of AlphaGo. That if you'd actually added a human operator, I think it would have won. It would have completely swept the series. So I think Go is probably still in a state where human-computer hybrid would be better. And I think it was also interesting to learn that they bootstrapped AlphaGo off of lots and lots of games played by strong humans on a server, right? So the initial definition of the problem was predict what a human would play in these records of high-quality humans playing each other, right? And from there, it trained and got better and better. But they were talking about the Deep Go folks were talking about we'd be interested to see if we could do this without bootstrapping, but we couldn't do it yet. So I think training data actually really mattered for making AlphaGo work well, and I think human in the loop is still really important for applications like Go playing, or even boring applications like support ticket classification or making cars drive on their own. So thanks. My Twitter is at L2K, and I'd love to talk with you guys.
All right, we have a few minutes for questions. There is a break after this talk, and the next talk starts at 4. So if you want to hang out and talk with Lukas, that's fine. And right now, if you have questions, raise your hand and talk into the mic.
Okay,
Let's give one more hand and a round of applause for Lukas.
Thank you.